So yesterday we outlined the life of a star. Now, we weren't considering all the stars in the universe, we were just considering stars that are average in size. Today we're going to start using the mass of the Sun as a point of reference. The mass of our Sun is approximately 1.989 times 10 to the 30 kilograms. Everything that we said yesterday, or explained yesterday, that formation of a star and then eventual death, finalizing in a white dwarf star, would pertain to any regular star, any star that's less than 8 times the mass of our Sun. Today we're going to talk about stars which are 8 times greater than the mass of the Sun. And what we're going to do is we're going to talk about, firstly, that generation of energy, the fusion process, because this is where it becomes very different. Now, all stars behave in the same way up until that point where the core starts to generate carbon. As we outlined yesterday, there was a pattern of behavior. The core in the center is made of hydrogen normally. That hydrogen fuses to become helium. Now, when the core is full of helium, then two things happen. The outer shell, the next shell here, starts to make helium. So it starts to change hydrogen into helium. That creates or generates a huge amount of energy and heat, and that forces, or that enables more like, the core then to fuse the helium together and make carbon, right? So carbon is being generated in that center. Now, with a regular star, any star that's less than 8 times the mass of the Sun, the process stops there. Carbon cannot be fused. There's not enough energy in that star to force the carbon to come together. But if that star is enormous, right, then the sheer pressure of all that matter surrounding the core does actually provoke a continuation of that fusion reaction. So what we get then is in the center, the carbon starts to fuse to make neon. The next shell begins to synthesize carbon. It begins to force the helium together to make carbon. Now, there is enough heat then radiating out to prompt the next shell, the next area or layer, to then fuse helium, and then the next layer to fuse hydrogen. So what you're getting is a repeat of the process outlined yesterday, but for more or heavier and heavier elements. That continues not just for neon, but then for oxygen, and then for silicon, and then for iron, right? So it's not just hydrogen, helium, and carbon that can be found in these stars, but a whole range of elements. And in fact, the process ends with iron because iron cannot be fused together. You should remember from topic 7 that iron is the most stable element. Iron is the one that requires the most energy to fuse with another iron nucleus. So therefore, it's harder for it to happen. So once that process ends with iron, once we cannot generate more heat here because fusion can no longer take place, then a big star starts to die. Now, if we go back to the idea of how the forces balance in a star, we can see why the consequences are so dramatic. The core here is now no longer generating that radiation pressure and that gas pressure out. So the gravity is way, way bigger than any forces that are being generated. And so considerable that they actually overcome that electron degeneracy pressure. And so the entire star collapses, but not in the same way as it did in the previous situation, where you had a collapsing and a flaring out of energy. What you have now is something way more dramatic. You have a supernova. The entire star explodes, basically. After this supernova, you have only two places to go. That core is a hyper dense core, which can either turn into a neutron star or a black hole. Now you've watched some videos on both of these, so I'm going to assume that that piece of work can take over now. You have an understanding of what happens after that supernova. But what I'm going to look at now is we're going to look at the actual numbers involved. So three names really stand out at this stage. We have Subrahmanyan Chandrasekhar, Robert Oppenheimer, and George Volkoff. These three are the ones who pretty much delineated the sizes at which these stages occur. Now, this is a very good way of visualizing the entire thing. Main sequence stars, there are two very clear limits. At 8 solar masses, we have what's called the Chandrasekhar limit. At this size, we go from a white dwarf situation, the red giant becoming a white dwarf and then shedding that planetary nebula, which we came across or we discussed yesterday. And over 8 to 8 solar masses or more, we now reach a supernova. The supernova will either lead to a neutron star or a black hole. Now for this, we require another limit. And that limit is the Oppenheimer-Volkoff limit. At 20 solar masses, so we're talking about stars that are 20 times the mass of the sun, the red giant supernovas and becomes a black hole. Anything under than that, or below that, under that or below that, is a neutron star. Okay. Now, those two limits, the 8 solar masses and 20 solar masses, can also be considered not by thinking about the mass of the main sequence star, but also interpreted in terms of the size of the white dwarf. If the white dwarf is 1.4 solar masses, right? So it's 1.4 times bigger than the mass of the sun, that would be a neutron star. And if it's actually 3 times the mass of the sun, then it would be a black hole. Now, it's probably easier to consider it in terms of a main sequence, but this explanation does give us a nice perspective on looking at the actual size of a white dwarf and how tiny white dwarfs are. A star of a mass 8 solar masses would be equivalent to a white dwarf of 1.4, which is quite a considerable decrease in mass. Okay, so what you need to be able to do is describe the stages in both types of star and also be able to understand how these two limits decide the eventual fate after the red giant phase.